Welcome to the last lecture of this week. Today we will talk about the free vibration analysis of symmetric cross ply laminate, which is simply supported. So, we have a laminate which is cross ply in XY system, X, Y, Z, and this is a cross ply laminate simply supported, simply supported, simply supported, simply supported all over. Now, here we are neglecting I1, the terms associated with I1 are neglected. So, with that I can solve the last equation. There are 3 equations of motion. I can solve the last equation separately. So, from the last equation we got this in the last class. So, with this we have to find out the natural frequency and vibration modes of a laminate, cross ply laminate simply supported. Now, again we make an assumption. Our assumption was a u as a function of x y t was summation j equal to 1 to L phi u j and a u j, and v is equal to j is equal to 1 to m phi v j a v j, and w j is equal to 1 to n phi w j a w j. Now, with that assumption this equation we write it like this. So, here we already had put the assumptions. Now, mx if I write in terms of the derivatives of displacement components, it looks like this. Now, mx has a negative sign. So, mx is minus dxx into del 2 w by del x2 plus dxy into del 2 w by del y2. So, that negative sign is adjusted. So, everything is, so this is plus here. Now, what we will do here is we will make some we will do the actual approximation. So, w we wrote as summation j going from 1 to n, and we had phi w j which is a function of x and y, and we had a w j which is a function of time. Now, instead of this here again like we did for the buckling problem or the static problem, we will make the use of double Fourier series. So, w as a function of x, y and t, we would write this as summation n going from 1 to n, m going from 1 to m, and then a pure function of x, mth function, and a function of y, and then multiplied by wmn. So, what again we are doing is we have m number of functions of x and n number of functions of y, and we are making their combination. So, this was represented as a single series and this is represented as a double series. So, the n here does not mean n here. So, n here corresponds to m n here. So, if I expand it, it would look like x 1 as a function of x multiplied by y 1 as a function of y plus x 1 as a function of x multiplied by we have to multiply w 1 1 also, multiplied by w 1 1 plus x 1 as a function of x multiplied by y 2 as a function of y into w 1 2, and it goes on up to x x m as a function of x into y n as a function of y multiplied by w m n, and also we represent w m n as w m n bar into e to the power I omega t. So, when we take derivative of w m n bar, it becomes minus omega square w m n bar into e to the power I omega t, and we can write this as minus omega square w m n. Now, this particular problem is a simply supported cross ply laminate. So, the boundary conditions are at x equal to 0 and x equal to a, we have w is equal to 0, and also at y is equal to 0 and y is equal to b, and there are natural boundary conditions, but here we satisfy only the essential boundary condition. If we can satisfy the natural boundary condition, that is better, but again that is not a requirement. So, for that we approximate x m as a function of x as sin m pi x by a, and y n as a function of y as sin n pi y by b, and we know that this kind of approximation satisfies the natural boundary condition also, because the laminate is simply supported, and also because we are neglecting I. So, because I 1, so u 0 and v 0 are not needed. Now, if we put all the approximations here, it looks like this. So, we have dropped out I 1. So, there is no terms associated with u 0 and v 0, and there should be a omega square here. So, if I look at this term, those two terms are not needed now. If I look at this term, so this term is just the approximation function multiplied by the derivative of the unknown constant associated. So, that is what we see here. We have I 0, the approximation function, here it is x I into y j, and multiplied by the derivative of the unknown constant. Similarly, we have I 2 here. So, the second order derivative of the approximation with respect to x multiplied by the derivative of the unknown constant, that is what we see here. So, this is the second order derivative. We know that if w as a function of x y t is equal to summation of n is equal to 1 to n, m is equal to 1 to m, if we have m x m y n into w m n. So, this tells me that del 2 w by del x 2 is equal to n is equal to 1 to n, m is equal to 1 to m, del 2 w by del x m by del x 2 into y n into w m n. We have seen this in the last week also, and accordingly we can do del 2 w by del y 2, n is equal to 1 to n, m is equal to 1 to m, and we can write x m multiplied by del 2 y n by del y 2 into w m n, and we can define a cross derivative del 2 w by del x del y, and which we can write as n is equal to 1 to n, m is equal to 1 to m, and we can write that as del x m by del x, del m del y n by del y into w m n. So, that is how we have done it here. Wherever we have the derivatives of W, we had put all these things from these expressions, and finally, the expression looks like this. And again, in these terms, inside the bracket, we have used I j as the indices. Similarly, when we wrote m x, m y and m s, we have used I j as the indices, and at the outer we have used the indices m and n. That is just to distinguish, because initially these terms were associated with delta W m n. Now, we are saying that the coefficient of delta W m n is 0. So, whatever was directly associated with delta W m n, the corresponding indices are m n, and inside we have I j. Now, this gives us this is the free variation equation for each m n. So, again this is the same equation written here. So, if we solve this equation, we can find out this omega square, and from the omega square and we can find out the eigenvectors, the mode shapes also. So, this equation would look like this. So, there are total m n linear simultaneous algebraic equations with omega as unknown. Now, if we write it, finally the equation will look like this. There will be a matrix K, and the matrix will have size m n multiplied by W bar is equal to a matrix M multiplied by W and omega square. Now, if our approximation is such that while calculating these integrations, these terms become 0 when I and j does not match, when I and m does not match, or j and n does not match. In that case, we will get uncoupled equations, but if that orthogonality condition is not valid based on the approximation, then we will get all the equations to be coupled. Now, in this problem we have used trigonometric functions with sin. So, we will get uncoupled equation. So, let us look at some numerical example. So, if we have a symmetric cross ply laminate with lamination sequence 0, 90, 0, 0, 90, 0, and each ply is 0.2 millimeter thick, and then we have Q matrix for each ply as 149, 3, 0, 3, 10, 0 and 0, 0, 6, and we have density rho for each ply as 1.6 gram per centimeter cube. Then with that we get the K matrix as a diagonal matrix. It is uncoupled because our approximations are sin approximations which satisfy the orthogonality condition 0, 4, 7, 5, 0.4, 0, 0, 0, 0, 4, 7, 5, 0.40, and we have 0, 0, 0, 9, 4, 7, 6, 6. This is the K matrix, and the mass matrix, the M matrix that we get is 0.48, 0, 0, 0, and then we have 0, 0.48, 0 0 0 0 0.480 0 0 0.48. So, after we solve it, we get 4 values of omega square. In fact, we can see that each equation is uncoupled. For example, in the first equation we can write 592.3 multiplied by W11 bar is equal to omega square multiplied by 0.48 W11, and likewise we can write for all the separate equations. If they were not uncoupled, I mean if they were coupled, that is also not a problem. We could have just solved the eigenvalue problem as we solve it and found out the 4 values of omega square. So, the 4 omega square that we get is omega, not omega square. We get omega square and then we can take root of that and then we get omega. Those are the natural frequencies. So, 35.127, it is radian per second. If I divide by 2 pi, we will get hertz, by the 99.48 radian per second, and then we have 99.48 radian per second. We have 140.51 radian per second, and the eigenvectors that we get is 1 0 0 0 transpose. So, that means the corresponding eigenvector is sin pi x by a, sin pi y by b. For the next one 0 1 0 0, the corresponding eigenvector is sin pi x by a, sin 2 pi y by b, and here we get 0 0 1 0 t, and the corresponding eigenvector is sin 2 pi x by a, sin pi y by b, and we have 0 0 0 1 transpose, and we have sin 2 pi x by a and sin 2 pi y by b. Now, here again because they were uncoupled, so we get the eigenvectors in this form. Otherwise, we could have populated some of the other components of the eigenvector also. Now, when we solve this problem, our approximation was W as a function of x y t is equal to summation of n is equal to 1 to 2, m is equal to 1 to 2, W m n sin m pi x by a and sin n pi y by b. So, by expanding we could write this as W11 sin pi x by a sin pi y by b, W12 into sin pi x by a into sin 2 pi y by b plus W21 into sin 2 pi x by a sin pi y by b plus W22 into sin 2 pi x by a multiplied by sin 2 pi y by b. So, this was the result from this example. Now, this is a generic approach using which using this any other type of problems can also be solved. There can be change in the laminate type, there can be change in the boundary conditions, according to we have to make suitable assumptions, and then we may or may not get uncoupled or coupled equations, and accordingly we have to solve it. So, this concludes the discussion on free vibration of composite laminates. Thank you.